Hello, we are speaking to John Mindy and Seong-jung for the term project in CS572 Intelligent Robotics. In this video, I will present term project proposal. I will first introduce the topic and background and related works, and I will choose our paper, and then Jung-min will explain the methodology as well as the experimental result. And finally, Jung-woo will outline our replication and improvements plans. What is imitation learning in nature? As you can see, the baby who learns some skills by imitating people in front of her in the video. Intelligent beings, including humans, tend to learn imitation without extra supervision and can transfer the learned skills to an unseen environment. This is an extra instinct that saves a lot of time and effort. In addition, they can then easily learn lower tasks with their learned inputs. Therefore, their copy and research attempts to train robots to imitate skills in videos efficiently. In particular, using reinforcement learning by providing a rich reward system. However, deep reinforcement learning method typically learns solutions from scratch for every task and often rely upon linear and method to view tasks in general, because its policies and presentations are task-specific, which means that this approach is not only inefficient, but also limits the versatility and adaptability of the system that can be built. In addition, in a typical robot task, each agent's behavior is often treated as a discrete action. However, in reality, tasks and skills are continuously learned like humans. Therefore, the concept of continuum of skills was introduced. As a related field in self-supervised robot learning, aims to learn task-independent skill embedding for multi-task environment without annotation. Several works use contrastive learning, learned predictive model, and perceptual reward functions. Popular simulation environments include HyperLab, OpenAIG, Mujoko, and PandaGym, and some widely used RL algorithms include PPO, DQN, DDQN, and AC, as shown in the figures on the right. We choose the paper Adversarial Skill Network because it presents a label-free robot skill embedding learning framework. The learned embedding are transferable real-world robot tasks, can be evaluated using synthetic and real-world datasets. And finally, the code and the datasets are publicly available. ASN proposed an unsupervised skill learning framework from video inputs. The learned embedding from ASN can be then transferred to learning skill by RL. The author of this paper provides the code base for your work, but there are some constraints. Since static dataset is not available, we will be using only the real-world data for both training and testing. As you can see in the video, the agent should be able to learn a novel task from the learned embedding from the two trained tasks.
Now I will introduce how they implemented these techniques. The key contribution of this paper is learning task-independent skill embeddings from multiple training tasks. To achieve this, author introduced a novel entropy regularization by jointly training two networks in an adversarial manner. The first one is an encoder network, and the second one is discriminator network. Given two sequential frames V and W, which are separated by a temporal stride delta t. They define an unlabeled skill embedding small x and collection of skills as a large X representing the different tasks. The encoder network embeds single frames of image into n-dimensional vectors, and the discriminator network takes two concatenated embedded frames that define an unlabeled skills X as an input and output Y. The probability of the skill being originated from the task C. The encoder parameters are updated using a metric learning loss and maximization of entropy of the discriminator output. Given two view pairs, V1 and V2, synchronize the videos from different perspectives. ASN attract frames that represent the same temporal task state and repulse temporal neighbors. By penalizing large distance of positive view pairs, they aim to smoother transition between similar states in a RL setting. The discriminator network minimizes the entropy given an unlabeled skill embedding X to be certain about which task C the skill originated from. The encoder tried to maximize the entropy HPY given X and D, which at the optimum will result in uniform conditional distribution over task classes. Finally, ASN optimized according to the three losses, KL divergence, discriminator, and embeddings. Here are the details for the experiments. You may pause the video to read this. ASN use simulated data sets of task A and B, A, B, and C, and demonstrates using different tasks D. For testing, they use videos of blocks of unseen sizes, textures, and backgrounds. Using these data sets, author evaluates the model performance on the view alignment score as shown and compared to that of TCN model. In contrast to TCN trained on multiple tasks, proposed model gets very close to 0.099 despite not being trained on the task. Finally, based on pre-trained embedding networks, they conducted control policy learning experiments. The proposed method succeeded in solving the tests, whereas baseline TCN approach converges to local minima. This demonstrates the effectiveness of ASN in the using skills for a novel task given single video demonstration.
Our plan for improving the performance includes the following. First, introduce latent variables for entropy regularization. Second, traditional projection approaches. Third, introducing auxiliary tasks. And fourth, fine-tuning in the embedding network with agent view frames. In the first approach, you can add an entropy regularization term H to the reward function in the policy learning, as you can see in the red box. The second approach involves additional learning of task-independent projection mappings from one domain to another, such as random projections and unsupervised manifold alignment. And the third is a popular approach, self-supervised learning, which targets learning good representations using unlabeled data as seen in the figures and transferring the trained model to downstream tasks. We often introduce pre-tasked tasks such as jigsaw puzzles and image colorization for pre-training the network. Also, we have a temporal shuffling that can be applied to video inputs. We can also try fine-tuning the embedding network using manually acquired agent view image frames to better suit our network to its domain. Here, we outline our plan for the three major tasks: environment setup, network implementation, and further simulation experiments. Thank you for listening.